My name is Timur Bashirov. I will be the voice at the other end of the webinar for the next hour or so. Start this presentation. So before we start, I'd like to speak about a couple important things. First of all, the goal of this seminar is to help users understand what exabyte.io is and how to benefit from using it. We have two recurring webinar series. The first one happens on first Friday of the month, which happens to be today, and it's for getting started. And the second webinar series is about advanced topics. So we are right now in the first getting started series. Every participant should be a registered exabyte.io user. If you are not, please navigate to platform.exabyte.io/register and create an account. So you can follow the presentation and do what we do in this presentation on your own. Every participant will receive this presentation on PDF, and highlighted text in the presentation will be linking to documentation, to videos, to additional information about how to do certain actions. This webinar is recorded and will be made available online after we're done. So before we start, there are certain ways to communicate back, to ask any question during the webinar. And there will be two time zones during the webinar where we will look through the questions and answer them. There is a chat button that you can use to ask questions. Please do that, and then we'll accumulate them in this chat window, and we'll go through the questions at the dedicated time. Okay? We will assume that the user is exploring the Exabyte platform and would like to learn more about its vision, capabilities, with a hands-on demonstration of the features. And we'll assume that the user is familiar with the basics of computational material science, like the file formats, modeling techniques, and such. When we will exclude advanced topics during this webinar, we'll cover them in the advanced topics series. For example, command line usage, programmatic usage, computational infrastructure will be all covered in 2 weeks in the advanced topics webinar series. Here is the quick agenda for today. We'll go through the overview of Exabyte platform and its capabilities within about 15 minutes or so. Then we will speak about the core parts of the platform. What we see is that by understanding the core parts, users can form a comprehensive view of the platform, and it can help them achieve specific goals faster. So we'll speak about what is that we have under the hood in the platform, what are the common user interface components and actions, and a little bit about the accounts and the service levels. And then we will focus on materials, workflows, and jobs in more details and go through the actions that pertain to each of these entities. Okay? All webinar participants, as I mentioned, have access to the webinar account in the Exabyte platform. This account has initial balance and advanced features enabled for it. So during the webinar, to save time, we will only see recorded videos of the functionality, but users can follow the presentation in PDF or over the video and perform exactly the same actions using the webinar account. Okay? All right. Here is a quick tip on how to access the webinar account. You can use the My Accounts switcher in the right-hand sidebar. So open right-hand sidebar, click My Accounts, and then click on Webinar to start using the platform as its member. Okay, so we'll start with the overview of the Exabyte platform, what it can do, what's the vision behind it, what is under the hood. What is that? What is Exabyte platform? It is a digital ecosystem that brings together experts with backgrounds in multiple different scientific fields that pertain to material science. And we have multiple concepts or features that the platform has to possess, including that it has to be collaborative, it has to cover multi-scale simulations, it has to be scalable in terms of the computations that we run, it has to be data-driven to enable machine learning and artificial intelligence approaches. And that brings things like experimental validation when we have collaborative aspects of it. It reflects on the complexity of material science research that we do. It can run realistic models, and it can enable non-analytic models as well using machine learning. So naturally, we start with the cloud as the focal point, as the point where multiple different expertise levels meet. And we have computational scientists, experimental scientists, data scientists, the infrastructure administrators, and the management, all meeting together in the cloud. That's how we think about it. And we have to have multiple different simulation tools or computational tools in general. That could be both built in-house, that could be commercial, that could be open source. And all of them have to feed into a single data platform. So the calculations that we do, the computational research has to be stored and organized so that we can enable machine learning approaches. And all of that has to be done in a secured way. So how do we enable something like this? We first start with a set of data standards. And we start with data standards that are open source. So we develop and maintain a set of open source components that together form the foundation of a fair R&D ecosystem. Fair is the term that is used largely to understand and classify the data that's findable, accessible, interoperable, and reusable. And the data standards that we have represent the entities that we work with inside the platform, such as materials, simulation workflows, calculation jobs, and material properties. We are implementing these standards in an object-oriented extendable way, and we separate these entities on purpose to improve the modularity and cover multiple models, multiple material types, at multiple scales. The data structures are implemented in a JSON schema format that is widely used on the web and are all available inside an online GitHub repository. We also have extractors that provide a way to convert into these standards that we develop from other existing sources. We have examples put for density functional theory calculations also online on GitHub. Applications finally allow users to utilize the data format to create the applications that can edit materials information. And we have examples for solid state materials design, again, present on GitHub. Now, open source components are used to build the publicly accessible online platform that you can access at platform.exabyte.io. And these components can also be licensed and further deployed in a private cloud scenario. We start with a computational material scientist as the most well-known to us usage scenario. So the computational material scientist, using multiple different varieties of tools, can feed the data into the platform through an extractor and a RESTful application programming interface, so that other users can see the results and exchange feedback with the computational scientist. Now, the second and third type of usage come from the data science domain and experimental science domain. So adding the data scientist allows to build analytics and machine learning focused knowledge. And adding experimental scientists to the platform allows to accelerate time to validation. So collaboration between these three different types of users is what we enable within the platform. And finally, adding external computational, experimental, and data platform elements completes the picture. Most of the time when we deal with someone who does this type of research, they already have external elements that they have deployed on site. It could be laboratory equipment, it could be high-performance computing infrastructure, and those can be connected to feed data into the platform. Okay. So this is the diagram that represents the vision behind exabyte.io. And if you look at the digital materials R&D cycle in a high level, we'll see that there are multiple different activities that scientists have to perform. And these activities can be summarized inside the cycle. And they are, essentially, there are 7 of them. They include designing material structures on atomic molecular level, designing modeling workflows, provisioning high-performance computing infrastructure, controlling and asserting the completion of the calculations, collecting the data in the structured storage, building analytics, and feeding experimental validation. So today, the platform that we have developed supports 1 through 6 already, and we have 7 on the roadmap as well. So here is the platform, how it looks to the user. Excuse me. There are multiple different entities that we store and organize, as you can see, like materials, workflows, and jobs. There are users that can collaborate on editing those entities, and there are certain computational infrastructure that is available to these users. Here is a quick example of point number 1 in how users can design new materials from atoms up. So we're looking at an aluminum gallium arsenide surface that was designed inside the platform. And here we can see how we can tag the information and store some metadata associated with the surface to be able to navigate and search for it in the future. So here is the crystal basis. You see the calculation cell, and there's certain metadata associated with this material structure. When we have multiple structures, like during studying chemical reactions, we can store this information as well. And here is a quick demonstration for an energy storage material. If you look along this line here, you'll see that the white atom that represents hydrogen is moving, which represents a certain chemical path. And these are the snapshots. There's 5 of them in this particular case at the different parts of this chemical path. And these are notched elastic band calculation images. So the second point, as of how we can design and set up simulation workflows and jobs, is demonstrated quickly in this video. So this is a band structure calculation. We can set up and choose the workflow for the electronic band structure. And we can apply this workflow to the material that we have just designed before. So we designed the aluminum gallium arsenide surface, and we have selected and applied a workflow that does the band structure calculation for this material. It also includes setting up things like the computational infrastructure, the number of cores, the time limits, and such. And then the third part is when we run and assert the completion of the simulation itself. So here you can see that we have submitted it to the computational infrastructure. We can monitor the progress of the calculation. And at the end, when the calculation is finished, we can see the result, which is the band structure plot itself. When we deal with something like nudged elastic band calculation, we obviously get a different result. So here is an example chemical reaction profile, where we can get information like the energy barrier and transition state. Now, many advanced computational scientists prefer to have programmatic access to the functionality to be able to collect the data and control the calculations from tools like Python. And here is a quick example where we have Python code on the right and what happens inside the platform here in the left top corner. And what we do here is we create materials and run calculations for them programmatically. And we can see how we can import materials and create them inside the platform. We create jobs for them, submit them for execution, and then wait for their completion. And at the end, when the calculation is done, we can extract the information from these calculations and form a pandas data frame in this case, which is handy when we want to do some analytics or create a machine learning model. Okay. The sixth point is about building data analytics tools. And for that, we have implemented inside the platform support for Jupyter Notebook. So here you can see that we started the calculation with Jupyter Notebook as an application. And then we can open Jupyter Notebook and edit it in real time. It requires certain parameters like account IDs and authentication tokens. And by putting these parameters, we are able to communicate with the RESTful API through this Jupyter Notebook session. And if you run this particular one, you can see what happens is that we have a query where we extract all the materials that are accessible to our account that have the formula that contains silicon. So essentially at the end, when we run this notebook, we get a list of materials. You can see it's an array. All of them, all of these materials have silicon inside the formula. There are certain applications that we support today, and there are certain access scenarios to these applications. First of all, we support access scenarios through the main interface, the web interface itself. And then we have support for alternative access modes like remote desktop or command line interface. The list of all the applications is available online in our documentation and includes things like Quantum Espresso, FAST, LAMPS, and WCAM, and such. There is also a set of analysis tools like VMD, Xgrist, and Vesta, and we can quickly install additional ones when users express the need. There is also support for shell scripting and Python, both inside the main user interface of the platform and on the command line level, of course. On the command line level, we have support for environment modules. And here is an example list of the modules that we support today. So this is a snapshot of command line module avail command. And then there is, of course, batch scripting to be able to communicate with the resource management system on the command line level. So all of this information is available at the links here. So here's a quick example of how we can submit the calculation through command line. So we open the web terminal session in this particular video, and then we navigate into the computational directory. We edit the job script, setting up certain parameters for the resource management system. And then we submit this job script for calculation. We monitor its progress, and at the end, when the calculation is done, we extract the result. Okay, so that's the command line usage scenario briefly. So here is a quick summary. Midway, exabyte.io is a comprehensive ecosystem for materials and chemical R&D that is essentially transitioning today's prevalent siloed or isolated approach to the fair, findable, accessible, interoperable, or usable infrastructure. The goal of the platform is to supercharge computational scientists to accelerate the way that they work today and connect multiple units together: data science, computational science, infrastructure. Today, computational material scientists mostly focus on delivering the insights about materials, and they minimize any kind of time and work spent on building the software tools, which leads to the siloed and isolated approach, where tools are disconnected for the most part. However, the increasing materials requirements and the advent of machine learning, availability of databases, poses new challenges when tools are disconnected. And that's why our platform can provide a solution, a flexible foundation that can be adapted to the needs of particular organizations. The platform can be accessed on multiple levels: infrastructure for compute only, programmatic level, and the web interface. So there are certain core parts that I'd like to go through next. And by understanding the core parts, users will be able to form a comprehensive picture of the platform and then understand its capabilities in more details, navigate the capabilities easier. First, we'll speak about what is it that we have under the hood. And if you look at the diagram of the platform in a bit more details, we'll see that there are multiple components. And these components, they essentially contribute and correspond to the open source repositories that we have on our GitHub page. So this is our organization's GitHub page, and you can see that the standards that we have on the diagram, they correspond to the repository number 1, SE, and the extractors are implemented in the repository number 2, exaparser. Applications, an example for it is given in repository number 3, materials designer. And RESTful API, or the examples of working with RESTful API, are denoted by number 4. So by looking at our GitHub page and looking at the open source code that we have there more in detail, so you can understand the implementation of each of these components. Now, there are certain entities that we deal with, and we identify at least 4 different types. The materials, or the structures, the modeling workflows, the simulation jobs, and materials properties. So materials and workflows together form a job that can have properties derived from it. So a job can calculate certain properties, and P on this diagram denotes the job properties. And then when we speak about the job itself includes a certain computational infrastructure, includes the workflow and compute parameters to be complete. We separate these entities on purpose to improve the modularity and cover multiple models and material types. There are still, this is still work in progress, so the boundaries can sometimes be blurry, but the data structures are very well defined, and they are represented inside the GitHub repository ESI that I mentioned 2 slides ago. They're based on the JavaScript object notation format, and we have a set of schemas that define the data structures themselves and the relationships between them. Again, this is fully open and that can be used as Python or JavaScript packages for the projects that you write in either of these languages. And we encourage the contributions from the community. So here's an example schema, an example for the data structures that we store. This is representing a material. So we have a material here whose properties include things like its formula, unit cell formula, basis, lattice, derived properties, and more. So in this particular example, we see that the basis contains material coordinates and element types, and as well as some additional information further down. So here's an example. This is how the data is structured inside a schema. Now, why it's important to understand that we have data standards and schema, it's important to understand that because under the hood, the platform deals with this information. So there is a way to access this raw information in a way that's represented here. So for example, if we look at the list of materials and we expand an entry in the list, we can see the exact representation of the data standard that we just discussed. For example, here is basis containing elements and coordinates in a contracted way. Okay, so every entity that user encounters inside the Exabyte.io platform is defined inside the Exabyte data convention and is available as an open source GitHub repository. The definitions are meant as a unified format, able to incorporate data from multiple material types, including crystal, molecule, nanostructure, etc., and multiple modeling approaches like density functional theory, molecular dynamics, Monte Carlo, and such. The platform provides a user interface to work with the entities and gives an alternative access options like command line, remote desktop, and RESTful API. There is a way to contribute new functionality to either of the 3, either to the data standards, to the applications, or extractors by communicating with us on GitHub. So you can put up a pull request, you can fork the repository and put a pull request that we will review together. And when we agree on the code, we will adopt this functionality and deploy it on the platform. We have created the foundation that can be built upon to incorporate other material types and modeling approaches. There are multiple components of the Exabyte platform that are open source and can be extended by the users. So if you don't support something today, then with your help, we can support it tomorrow. Users may edit the code to implement desired features and put up pull requests on GitHub. We will review the code and incorporate this functionality into the platform online. Okay, so now let's speak a little bit about the user interface components as they look today. So here is the main user interface components of the platform. There is a header that contains things like navigation and these triggers for the 2 sidebars, the left-hand sidebar and the right-hand sidebar. There is a footer that contains links to documentation and some additional information, and there is a support widget in the bottom left. Excuse me, please. So if you click on a support widget that can take you to the documentation. Just one moment. So here is the support widget. And if you have any questions about how to operate the platform, we recommend submitting a support request. So this is how the support widget looks like when you open it. We advise users to provide their name and email address, of course, and include screenshots or screencasts of the problems, because that will help us tremendously to understand the exact issue, and it will save us time in communicating with you. There is also a chat widget that we have, which is on the right. The chat widget is meant for the people who are not yet logged in, are not yet registered users, to help them understand what the platform does and to help them register. So the logged in registered users should use support widgets on the left-hand side. Now, if we click on the top right corner here, we can trigger the left-hand sidebar. That's how it looks. And the left-hand sidebar contains links to the entities, such as jobs, materials, workflows, projects. And these entities essentially just represent this links navigate back to the account page where materials, workflows, and jobs for this account are stored. So these are the links in the sidebar will take users back to their account page. There is the right-hand sidebar that can be triggered by clicking at the name of the user here or the account. And the right-hand sidebar contains links to the account preferences, billing and payment information, and the additional remote access levels. So the web terminal, remote desktop, and such. And then there also is a set of entities related interface components. So the entities like materials, workflows, and jobs have these three general interface components that are used for them. And those are the explorer, or the list or table that represents the entities inside the collection. So users can explore and see multiple entities at once. And then there is a designer component whose purpose is to help in development and design, where the entities can be created or edited. And there is also a viewer component, which is a dedicated page that allows to view one or more entities to make small adjustments. So editing means making large adjustments, and adjusting means making small tweaks, for example, editing metadata like tags. So this is how the Explorer looks like for materials. This is the entity items list, or Explorer as we call it. And Explorer contains a set of actions that can be performed on each of these entities. For example, we can open a workflow entity in this list, we can copy it, we can delete it, update it, set as default. And the entities are the actions are duplicated. If we select actions on a particular entry here, we will only affect it. If we select multiple entries in the list and then click at the action at the top, then we will affect multiple entities at once. There is a way to search here at the top, so we can narrow down the list of materials, for example, by formula. And here is how an example materials designer page looks like. So this is the interface that I will cover a little bit more in details later. And it allows essentially users the capability to modify material information like crystallographic information or edit material in 3D. And here is a materials viewer, an example component that can visualize a material entry where we can see its lattice spaces and metadata. Metadata is editable in this page. A little bit about the accounts and sharing. So once we have the entities, we need to understand how to perform actions on these entities. And for that purpose, we have the accounts. Accounts own and can perform actions on the entities. Accounts define the different ways of how users can interact with the platform. And accounts have members, users. There are organizational or team and personal accounts. Personal accounts have only one member, the person or the user themselves. And the organizational or team accounts have teams that have different permissions on entities. For example, they can read or edit the entities. Account members have shared access to entities as set by account administrators. A little bit about the entity collections and the concept of the bank as we have it implemented. So entities are collected inside the platform in a way that each account has their independent entities separately. For example, if you create a material that represents silicon and somebody else creates the same material, these two materials will be completely independent and they will be owned separately by their corresponding accounts. However, to be able to track unique entities, we have implemented a concept that we call a bank. And there is a mapping function that will understand at the point of creation that the two materials that we have just created independently, in fact, represent the same material. And it will store a single entity inside the materials bank. There is an exabyte ID property that is associated with this entity, and it represents the unique materials by ID. There are certain public and private data access scenarios. For example, if an account X has private data enabled for it, and somebody from that account creates silicon as a material, then no other account will be able to see that material inside materials bank, unless they create independently the same material and they do not have the private data. So if an account creates a material and the private data is not enabled, then every other account will be able to see the entry inside materials bank. So this is a flexible way and secure way to collaborate and understand the unique entities that we have created. There is also a quick way to import entities from the bank. As our platform grows and there are more users, they create entities that are shared at the bank level. And we have implemented a quick way to navigate and import entities like workflows and materials from the bank. And we have a set of entities that are produced by the curator's account that essentially represents the platform administrators and provides usually high quality templated entities like workflows and materials. Workflows are handy for density functional theory calculations like band gap, etc. The way that accounts are governed is set inside the service level. So each account has certain service level associated with it. And depending on the service level, the features that are available to these accounts are different. For example, we have multiple different service levels, starting from a free service level all the way to the enterprise, which all have different subscription fees and compute allocation and things like the number of the cost for an additional member, additional disk space, ordinary compute price, and such. So here, this is a table that we have represented in the computational line too. And if you look at the quick comparison between these different features, then essentially what the difference is that the pro and team and enterprise account are meant for sharing. So when there's at least 2 or more people. And then there are certain access options like command line access that we have enabled for the pro users and things like support severity that differ between these different service levels. So a quick summary about the core components. The data standards are at the very core of the platform, and they define the entities that the platform works with through multiple access scenarios. These definitions are meant as a unified format, and if they can incorporate today density functional theory and crystalline materials for the most part, but tomorrow we can extend it together to include molecular information about nanostructures, and things like molecular dynamics, Monte Carlo, etc. The platform provides a user interface to work with these entities and gives additional access options like RESTful API or command line. The accounts can perform actions on the entities in a shared access way, allowing users to collaborate. And features available to accounts are defined by their current service levels, from free to enterprise. Okay, so I think I'm mostly done with the first half of this presentation. We're running a little bit over time, but let's see if we have any questions. I'm going to exit the presentation for a moment. Okay. Looks like no questions yet. So we will proceed forward with this presentation. I will speak about the entities more in details, particular entities like materials, workflows, and jobs. So when we deal with materials, there are certain actions that we can perform on them, and I will now demonstrate some of them and how we can access these actions inside the platform. So first of all, when we have a list of materials on the disk or our computer, we can upload this information into the platform to start working with it. And here's an example of how we can upload materials information from disk. So first of all, I click on the tool, on the action in the toolbar, and I select a set of WASP or postcard files from disk. I select these files and they're present now inside this uploader interface. I can quickly check that the information in fact is correct by clicking on any of these entries. So here is a postcard file that I just uploaded from my disk. And in the meantime, before actually creating the entities, I can set metadata for one or more of these entities inside this interface. So for example, it could be handy to identify certain files using tags. And here I am applying tag 1 and tag 2 to one of the files that I have just selected. And then I select all three of them and I click upload to create material entities inside the platform. When the process is finished, I see that the materials are created and one of them retains the metadata information, retains the tags. Okay, so here's a quick way, a quick explanation of how we can upload materials information in postcard format and attach metadata to it. Now, the second way to add materials information to the platform is by using an import function. And here we import from an online database, materials project in this case. For that, we use the import tool. It looks like a cloud with an arrow. And we search for the material that we'd like to import. In this case, I'm using magnesium dioxide to narrow down the list. And then select the material based on the list and click import. When the material is imported, you can see here the check mark that pops up. And the material entry is present inside our collection in this case. So when we navigate, when we open this material item, we are taken to the viewer page where we can see that this is in fact the material that we wanted to have in our collection. Okay, so this is the way to import a material from an online database. A third option is to import or copy a material from the bank. As we have just discussed, there is a bank collection where we store unique materials coming from multiple accounts. And there is a way to access this collection by navigating to materials bank page. So I opened the sidebar and clicked on the bank first, and then clicked on materials. And then I can search for magnesium dioxide inside the bank collection as well. And I can see that somebody have already created this entry. And I can click on copy tool in the top to copy this information to my private collection, which is exactly what this message is saying. It says the item is copied to your private collection successfully. When I navigate back to my materials list, You can see that magnesium dioxide has been copied there as well. Okay, so there are 3 ways to ingest materials information: by uploading, or copying it from the bank, or importing it from an online database. There is also a dedicated action for importing from the bank, which looks like a bank icon here in blue. Now, when we have a list of materials, we also need to search not just by formula, by potentially other keywords too. And advanced search functionality allows us to do that. So we can open the advanced search functionality by clicking on this advanced search icon in the top, which opens this query builder. And query builder represents an interface that has multiple logical rules applied together. And so there are rules, keywords that are connected by logical and or at multiple levels. And here we can combine multiple keywords together using an AND condition. So by the end of this video, we'll see that we are searching by formula, by volume that is less than 80 in angstrom cubes, and by tags as well, tags that contain high pressure. So here I'm narrowing down the list of materials to only the ones that contain a certain formula, aluminum, the volume of your unit cell that is less than 80 angstrom cubed, and entries that contain high pressure in tags. And here, as you can see, there's only one entity that's present after the filter. And when I no longer need the filter, I can reset it by clicking the corresponding button. So this is how we can use advanced search functionality to narrow down the list of materials to work with. Now, the designer functionality for materials can be accessed by using the create button. So create or edit interface, essentially we call them. We can start the materials designer session by clicking on this create button. And here is how it looks. There are four important components. First of all, there's a header menu that contains multiple submenus. There is an items list in the left, and there is a crystallographic data panel in the middle, and 3D viewer on the right. Materials Designer is also a standalone open source JavaScript application. So if you're building a web page, you can use this interface inside your web page. It's all open source. Now here's a quick example of how we can select materials to work with inside the Materials Designer. For that, we click on the header and on the input-output submenu, and we select the import option. And then we are presented with the list of materials that are stored inside our account collection. And here we can search for one of the materials and select it to be imported into the Materials Designer interface. As you can see, I started with silicon as a default option, and then I added another material here which contains aluminum. So I can remove the other entry whenever I don't need it anymore, and it will be removed from the interface, and it will still be present in the collection, of course. So this is just an in-memory session. Everything that we remove here still is present inside the database. Okay, so here is how I can extract the material information and put it into Materials Designer for further editing. We can do multiple things with materials here, like cloning, creating surfaces, creating interfaces, editing materials information in 3D, but I will wait for the advanced topic webinar to explain this a bit more in details. So this is just a quick overview of the actions that we can perform for materials. We'll proceed to speak about the workflows now. And just like with materials, the workflows also contain the bank. So the workflows bank is where we accumulate all unique workflow entries, unique by the logic that is included inside the workflow. And as we develop the platform further, there is a set of template workflows that are present inside the bank. And here's a quick way of how we can access those templated workflows. We will open the left-hand sidebar again and select bank and then workflows. Here we can search for the workflow names, for example, band structure. And we can also search for the applications or the names of the sub-workflow like convergence. And we can see that there is indeed a band structure workflow that is present already inside the bank. And we can click on copy to copy this bank workflow into our private collection. When we navigate back to the list of workflows, we can see that the band structure workflow is present there. Okay, so we can apply it to the materials that we have created. Now, to be able to edit the workflows and change its logic, we need to first understand a little bit more its inner structure. The inner structure of the workflows is made of sub-workflows and units. And you can think about the sub-workflow as a logical component that corresponds to a particular simulation engine, for example, Quantum Espresso or VASP. And together, inside the sub-workflow, there could be multiple units that represent a certain flowchart logic. Like here, for example, we run unit 1, then unit 2, and then there's multiple units that are run together during step number 3, like unit 3 underscore 1, 3 underscore 2, 3 underscore 3. And then at the end, all this information is merged together to run unit number 4. Okay, sub-workflows contain the model and method information as well, like density functional theory and pseudopotential as a method. And the concept is introduced for modularity to reuse the commonly deployed logic. The unit, as part of the workflow, is an elementary calculation that is executed in a certain succession to reflect on the logic inside the workflow. And we can do things like convergence, if-else conditions, or map reduce. Units have different types, like execution to run Quantum Espresso, assignment to assign a variable A equal B, and condition to be able to decide on where to go inside the flowchart. Execution units have executables like the w.x and flavors like the w.scf. This is again made for modularity and to be able to reuse these calculation blocks within multiple workflows. So here is how the designer interface looks like for the workflows. We have the header menu that represents the information about the workflow, and then the items list that contains multiple sub-workflows here. And then there is the sub-workflow panel. So we can select the sub-workflow in the list, and then we can edit the sub-workflow here in the editor panel. Here is a quick example of how we can add or delete sub-workflows from a workflow. We can click on this plus button in the sub-workflow panel, and we can select the type of sub-workflow to add. It says select unit type, but in this case, the unit of the workflow is a sub-workflow itself. So the unit can be a sub-workflow when we speak about the workflow itself, right? So here is a quick way to add a sub-workflow, and then we can delete it subsequently. When sub-workflow is added, by default, it's empty. And here is the sub-workflow editor interface in more details. There's an actions menu bar. There are certain editor tabs that include the information like the model and method, important settings, detailed view, the properties that are extracted, and there is a units flowchart that represents the units inside this sub-workflow. Here is the units flowchart in more details. The currently active unit box is highlighted in gray. Unit type is shown by its first letter. So E corresponds to execution. You can see here in the lower bottom corner. You can click on the unit to open its detailed view. But before we do that, a little bit more about the flowchart logic. So it might not be clear from looking at this list what exactly the flowchart logic is. And this is temporary. We will represent the logic in a flowchart like this. So this flowchart corresponds exactly to the logic that is represented here. So what happens is that we have an assignment unit, which assigns a variable in key is equal to 1. And then we have another variable, x equal to 0. And then we run the PWSCF calculation. We extract its output as the total energy. And then we see whether the condition is satisfied. The condition is that output minus x is less than the threshold. And we store x essentially is just a helper variable to store the output on the previous leg of this convergence iteration. So this is a quick way to implement something like key point convergence, where we increase the number of key points by 1 each time. And then we see whether total energy had converged with respect to the key point grid. And here inside the platform, we can see that there are multiple different types of units. Units like A corresponds to the assignment unit, like n underscore key is equal to 1. C corresponds to the condition unit, like output minus x is less than threshold. And E is the execution unit, as we already know. Now, when we open the units, we can edit the information that is contained in each one separately. When there is an application section where we can select things like the executables or flavors, we can select the properties that are extracted inside each of these units. We can select the monitors, like whether we'd like to see the standard output or the convergence graphs. We can select where this unit sits inside the workflow logic. So, for example, which unit will be next, or which unit will be before this one. And then finally, we can change the input templates, so the actual textual input information that is passed to the executable. And here is an important concept that we deploy. We deploy the templating concept to be able to pass the materials information into the unit input. And the way that we do that is by separating, again, materials information from the workflow information. So the workflow information by itself contains only the information that relates to the simulation workflow and no material information by default. Although this quantum espresso input file, for example, needs things like the number of atoms and the number of atom types, we do not directly pass them to make the workflows reusable, but instead we use helper variables. So the variables like input here, input dot and add, input dot and type, are actually constructed based on the materials information. So here is the metadata that contains input key. And inside the input key, there is another dictionary that contains iBraf and atoms and types. And here, that's what we call the template data. Material information is passed to form the template data, which is further passed to the workflow to render the template. And when we render the template, we get the actual representation that will be passed to the simulation engine, to pw.x in this case. And there are multiple levels at which the rendering occurs. There is the first render that happens on the web. It's for users to understand what type of material information will go into this. And as you can see, after the rendering inside the preview tab, we still have some variables like job, work directory that are not substituted for. And that happens because really on the user interface, users don't need to know which job directory this calculation will be running in. It's a system level parameter that is substituted at the second render or runtime. So the system automatically substitutes the workflow directory at the point when the calculation is started, and it feeds the final output to the simulation engine to pw.x. Okay. Now let's speak a little bit more about the jobs and demonstrate how we can use the material and workflow entities to perform the calculations. But before we speak about creating a job, there are certain conditions that have to be satisfied. First of all, we need to create, import, or upload the desired materials. create or import the desired workflows, and then assert that the account has enough balance to perform the calculations. Assert that the account has enough disk space to perform the calculations. Some of the calculations could be quite a bit demanding in terms of the computational parameters and the data requirements. So we need to make sure that we have enough of both. And then we need to navigate to the desired project. Project is how we organize the jobs. So usually when people work on a particular problem, they will create a project and run the calculations that correspond to that project inside it. And then we click on Create Job here in the right-hand sidebar, which takes us to the job designer. The job designer interface again has the header menu, where things like the job name can be set and job actions can be triggered. And it has materials, workflows, and compute tabs, where the corresponding information can be set. So we start with selecting materials. So when we open the job designer, it contains the material that we have selected as a default. So in this particular case, aluminum gallium arsenide slab is what I selected as a default material, and that's why I'm seeing it inside the job designer. If I'd like to select other materials instead, I can click on these three dots in the header to open the dropdown. And from this dropdown, I click on Select Materials and select one or more materials inside my collection. As you can see, I selected 6, and all 6 of them have been added to the job designer. And what it means is that the job designer in this case will produce multiple jobs, one of each for each material. And you can see there is a placeholder for formula that will be added to the job name automatically, because when we're done and we have created the jobs, it is handy to understand which job corresponds to which material, and that's why we retain the formula inside the name. Okay. So here's how we can select materials, and we can quickly visualize materials information inside the job designer. The next step is to select the workflow. And just like we did with materials, we can navigate back to the top, to the header, click on the 3 dots, and choose Select Workflow. And click on the workflow that you want to select. In this case, I'm clicking on the phonon density of states. Okay, click on Select Items in the top first in the modal, and navigate to the Workflow tab to assert that we indeed selected the phonon density of states workflow. The third step is where we set the compute parameters. And this could be quite a bit complex depending on the calculations. But in this presentation, I'm not going to go into more details. I'll just list the parameters that we can change. And those include the time limit for how long the calculation will be running at most, the clusters that correspond to different cloud providers, the queue types, the number of nodes to run this calculation on, and some advanced options like parallelization over key points, for example, as well as notifications. So I can select to be notified at any point when the calculation is started, aborted, or finished. After we set the computational parameters, we can click on the check mark at the top, check mark button, to save the job. Okay, so a few notes about the job's creation. Workflows cannot be modified during the job creation, and we did that on purpose to simplify the user interface component and to assert data consistency. Users should modify, edit the workflows first, and then select the modified workflow during the job creation. The unit input preview can still be edited directly inside the job. So if there's a certain flag that you'd like to add to the input, you can still do that directly inside the job designer. But we believe that it should be avoided to keep the metadata associated with the job consistent. Multiple materials can be selected for high throughput type job creation or for multi-material jobs like the nudged elastic band calculations, where we have multiple images, multiple material structures at once. Jobs can also span other jobs and wait for their execution. And this topic will be covered in a separate advanced topics webinar session. Now, once we have created the job, we can find it in the list of jobs in the Jobs Explorer like this. It will have the P status, pre-submission, highlighted in blue. And then we can select this job. And we can click on the actions for this job and select Run there to submit it. It will shortly change its status to submitted as, and after some wait time, it will change the status to active A. Here's a color coding, so it's bright blue, dark blue, and orange. Orange means that the job is started. Next, when the job is started, we can monitor its progress by navigating into it, and we'll see that there are multiple tabs present now: compute, results, and files. If we go back to the workflow tab and navigate to the unit that is currently highlighted in orange, the currently active unit, we can see the output of the calculation engine, for example, PWSEF in this case, and we can see the convergence charts as well that are updated in real time. Okay, and when the unit is finished, it is automatically turned green. So we can see that this part of the calculation has progressed successfully and had finished. At the end, when the calculation is finished, its status, the job status, is turned to finished and highlighted in green. We can navigate back to the job designer, job viewer, in this case, after the job is finished, and see its results. So the results panel contains things like total energy, pressure, Fermi energy, forces, and such. The files that are produced inside the calculation are present inside the Files tab, and we can click on each one to download it or to view it. Okay, so this is how we can run a job and access its input files and by using a material and the workflow that we have previously created. Okay, so now it's time for the Q&A. We're a little bit over time, but maybe we can take one quick question. Are there any questions? Okay, it looks like no questions at this point, so we'll consider this presentation finished. Again, everybody will receive a PDF copy of this presentation that you can follow on your own. And everybody can use the webinar account to perform the actions that we have just discussed, like create materials, create workflows, and run simulation jobs. Thanks, everybody, and we'll see you again in a couple of weeks at the Advanced Topics webinar.